Hello and welcome to podcast number 55. So, zipping along with these. This is a kind of continuation of the previous one, which we started alcohols with. Again, my name is Todd Bennett. If this is the first one you're watching, and that is a possibility if you're using this as a review course as opposed to a supplement to your current organic chemistry course. Then, just philosophically, my goal on these is to give you a review of the material if you've seen it before, or more importantly, just a good way to look at it, or just a way to emphasize the pieces that are really important, and whenever possible, to make it correlate to real life examples. And most of those real life examples for us in organic chemistry come from biochemistry, physiology, and pharmacology. So we will address some of that, but um, also some things that are foundation in chemistry in general and oxidation reduction you will find in GChem, you will find it in OChem, you will find it in biochem, you will find it in physiology, you will find it, heck, even in physics. Uh, Natural batteries are that. So the point being, very, very important topic. And so I want to start with just a review of redox chemistry. I'm going to call it carbonyl redox chemistry, but really, I can also call it alcohol redox chemistry. So alcohols can be oxidized up to carbonyls. Carbonyls can be reduced down to alcohols. So they're kind of in cahoots with one another. So oxidation reduction. You learned that possibly the phrase, very, very good one, but Leo the red cat says grr. That is mnemonic. If you try to convince me that oil rig is a good way to go, I'll probably have my typical little hissy fit over it because it is not nearly as good as this. This is why this one is so good. Lose electrons oxidation. So if you just say oil rig oxidation is loss, reduction is gain, we got to think deeper than that. For electrons, that's true. But for H's and O's, you have opposite behavior. So you can't just straight memorize it. So this one specifies that it's electrons. So lose electrons oxidation, gain electrons reduction, and the red cat. It's not Leo the lion says grr, it's Leo the red cat says grr because reduction occurs at the cathode. Absolutely critical. I think I might have mentioned this when it's popped up earlier. 99.99% of all of you watching this, assuming this is a cross section of people from all the different universities across the globe, possibly, but certainly the US, you covered electrochemical cells when you took GChem. Very, very, very few universities don't. I happen to currently, as of today, work at one that doesn't. So if you are watching this and you didn't cover this, this is an essential part of GChem. Why it wasn't covered, I don't know. But it is something that is heavily tested, and you're expected to know what it is because it shows up in future classes. But the anode and cathode, oxidation, oxidation occurs at the anode, red cat, reduction occurs at the cathode. So oxidation is loss of electrons. So you lose electrons at the anode, they flow over to the cathode where you gain electrons. So that's where reduction occurs. So red cat, reduction occurs. So things played out. Oxidation, they break down. Not going to go into the physiology, the biochemistry, the physics, or the general chemistry of it. Just going to focus on OChem. But this mnemonic will power you through multiple classes. If you're doing electrophoresis in biochem, red cat. Reduction occurs at the cathode, so cations go to the cathode where they get reduced. Cations go to the cathode, anions go to the anode. If you're doing electrochemical cells in GChem, absolutely critical to know that oxidation, electrons being lost occurs at the anode, so electrons flow anode to cathode. If you're doing physics, you have to know how capacitors are set up. You have to know which way electrons flow or current flows. It's critical. So know that mnemonic. Not an OChem topic, but fits in here anyway. For us in OChem, and I'm going to also drag biochem into this, we worry about what happens to molecules. So oxidation, we typically think of gain of oxygen. That's where the name comes from. So reduction is the loss of oxygen, and we want to emphasize loss of bonds to oxygen and gain of bonds to oxygen. But if you gain bonds to H, that a lot of times accompanies loss of bonds to O. So they kind of go in cahoots. So gain of bonds to H and loss of bonds to O kind of run in tandem, and gain of bonds to O and loss of bonds to H. So if you hydrogenate something, you've reduced it. If you dehydrogenate it, you've oxidized it. Oxidation state will go up from this. Oxidation state will go down when this happens. When you lose oxygen, lose bonds to oxygen, you have been reduced. Your oxidation state goes down. When you gain a bond to O, your oxidation state goes up. Okay. In GChem, you just have to know that this means a less electronegative atom. This means a more electronegative atom. But for biochem and OChem, pretty much we're going to just worry about H and O, and maybe on rare occasions, N. N can be treated like an O. Okay. Note, oxidation state decreases when you're reduced, oxidation state increases when you're oxidized. This is the important part. Okay, so how does this apply to OChem? So here's a series of OChem molecules, and just want to note that carbon and CO2 has a positive 4 oxidation state, so O's are -2 each. There's 2 of them, so that's -4. So carbon is a +4 oxidation state. On the other end of the spectrum, H's are -1 each. So -4 for the, sorry, they are +4 each. +1 each, so +4. So the carbon is -4. So that's where this number is coming from. I've chosen red for reduction, so it's fully reduced, mostly reduced, barely reduced, broke even, barely oxidized, mediumly oxidized, and highly oxidized. So I do red for reduction, blue for oxidation, just one of those color coding things I've done as a habit over the years, and it helps me to remember it. So a large, and I mean a substantial amount of organic chemistry, biochemistry, physiology, molecular biology, cell bio, you name it, involves the oxidation or reduction of molecules. We survive because we consume foods that get oxidized by oxygen, which means oxidation releases energy, reduction stores energy. This is a main staple of what we do. So knowing oxidation states matters. So I want to look at this table and note that carbon could be anywhere from -4 to +4. Nitrogen could be anywhere from -5 to +3. Just fun fact. Big part of organic chemistry and biology, I already mentioned that. I want to mention how this things works. So I'm going to start with CH4. It has 4 bonds to H, so every single bond puts a negative on the central atom carbon and a positive on the external atom H. And so it ends up with a -1, 2, 3, 4. -4 oxidation state. So 4 bonds to H and no bonds to O, -4 oxidation state. When it gets oxidized, it will lose a bond to H and gain a bond to O. So if I have this get oxidized, from here, it's going to get oxidized. So oxidation state has to go up from -4, it's going to go up. Every time you gain a bond to O, you click up once. Every time you lose a bond to H, you click up once. So if this were to go from methane to methanol, it lost this bond to H and it gained this bond to O. So by gaining bond to O, it changed by 1, and by losing bond to H, it changed by 1. So overall, it changes by 2, is now -2. So let me do the same thing I did before. Plus for carbon and minus for O in that bond. Plus for H, minus for carbon, plus for H, minus for carbon, plus for H, minus for carbon. So oxidation state, minus, 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 and plus. So it is -2. Perfect. Okay. So same thing. If I lose a bond to H, so it becomes 2 H's, and gain a bond to O instead of 1 bond to O is now 2. I will go to this compound. So again, I have gone from 1 bond to O to 2. So I gained a bond to O, and I had 3, and I now go down 2. So I lost bond to H. So my prediction, by gaining bond to O, it changed by 1. By losing bond to H, it changed another 1. So I predict that it's going to go from -2 to 0. That's what the table tells me it did. Again, I want to look at this as a minus and a plus. Minus and a plus. That's how those electrons are distributed. Plus, minus, minus for carbon, plus for H. You always put a plus next to the less electronegative atom in the bond and a minus next to the more electronegative atom in the bond. And then you see what it has for its net oxidation state. Plus, plus, minus, minus. It is a 0. Okay. And you know what? I'm going to go back. I apologize for changing my mind. I don't know why I erased that earlier. So I just want to show that the oxidation state can be obtained that way. So -4, just drew over that. So let me put that negative in there. Okay, so if you're seeing a trend, every time it goes down, so these are what sometimes referred to as oxidation levels. This is a fully reduced level, this fully oxidized level. You change by 2 every time you change a level. So the next level up is going to go to +2. So notice 4 H's, 3 H's, 2 H's. This has 1 H, this has no H's. No bonds O, 1 bond O, 2 bonds O. This has 3 bonds O. So this molecule right here is a carboxylic acid. It now has 1, 2, 3 bonds to O and 1 bond to H. So again, it gained a bond to O, lost a bond to H. So those are each responsible for 2 electrons. So now it is +2. Do the same thing. Plus, minus for every other bond. Plus on the carbon, minus on the O, minus, plus. Plus, minus for that bond. So that is now a +2. And then finally, when I go to CO2, 4 bonds O, 0 bonds H's. So again, it has gained a bond to O, lost a bond to H. So it is also changed by 2 electrons. Every single one is a minus, minus, plus, 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 minus, minus, +4, which means this is oxidized by 2 electrons, oxidized by 2 electrons, oxidized by 2 electrons, and oxidized by 2 electrons. This chart is incredibly helpful. You could have also gone from here to here to here to here, where every time you go up a level, you gain a bond to O, lose a bond to H, and change your oxidation state by 2 because you lost 2 electrons. We can also go the other way, reduce by 2, reduce by 2, reduce by 2, and reduce by 2, and get back to methane. Know this relative chart, and it will help you in every single class you take, probably even poli-sci and econ, a language class. Might be exaggerating with that, but it is incredibly helpful. Okay, so back to redox. These are generic terms, more specific to OChem. Oxidizing agents get reduced. So the common oxidizing agents you will see in OChem and or biochem are typically rich in O because they start with a very high oxidation state, so they can easily get reduced. Poor in H, so they can pick up H's. So by picking up H, if the other one loses an H, then it is causing it to get oxidized. But it itself gets reduced, but it causes the other compound you react with to get the opposite. So if something gets reduced, something else has to get oxidized. CO3 we're going to see very common. KMNO4 we already saw with double bonds. O3 we saw with double bonds. Ozonolysis, peroxy acids inserted O's. We saw it for an alkene. We're going to see it in carbonyl reactions, something called Geber-Villiger. Peroxides we've seen as causing oxidation. In bio, you may have learned about NAD+. It's poor in H, so it's going to pick up an H. When it picks up an H, it gets reduced, cause oxidation of the other compound. FAD can become FADH2. So these are common reagents. Notice again, they are rich in O, or they are poor in H, like these two. Reducing agents, exact opposite. They get reduced, they cause oxidation, or timeout, said backwards. They get oxidized, they cause reduction, as they are reducing agents. They are rich in H and poor in O. So lithium hydride we'll study, NaBH4, palladium and H2, you already learned that with an alkene. N2H4, we're going to learn how it reacts with carbonyls. So this we called, we'll be covering this one. I'm so sorry, I'm just throwing it up, but this one we'll cover. And then in biochem, NADH and FADH2, those are the partners over here. Okay, so hopefully that seems okay. So question, which of the following oxidizing agent? This should be as simple as lots of O's, oxidizes. Lots of O's, oxidizes. Lots of O's, oxidizes. Metal and H, no O's, got to be a reducing agent. So oxidation, 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 correction for the last one. Keep things that simple and you should be in pretty good shape. Okay. Oxidation reactions, just want you to just recognize if I treat this with an oxidizing agent, it gets reduced, but the other compound, this being the other compound, went from one bond to O here to two bonds to O there. So notice that changed from 1 to 2, it was oxidized. So pyridine, just point of interest, this in theory could put another O in here and go up to 3, but pyridine stops it at 2. That's going to be something that we will get to once we're a little more into the carbonyl reactivity, but I just want to allude to this, that we use specialty reagents to carry out certain types of oxidations. This is where memorization is going to kick in. So pyridine poisons it and stops it at just 2 instead of letting it go up to a third bond O. Again, oxidation state. I want to revisit this again. Carbon in our group is a carbon. This is a carbon, equal electronegativity, so they each get a 0. H and C, C is more electronegative, so negative on C, positive on H, negative on C, positive on H, and then O is more electronegative, so O minus, C gets a plus, so minus, minus, a plus, and a 0 means overall oxidation state is 0. This also works for oxygen, it also works for hydrogen, but focusing on carbon. It lost a bond to H, so it had 2 bonds to H, now it only has 1. Had 1 bond to O, it now has 2. So keep in mind for losing an H or gaining an O, that's 2 electrons. So oxidation state should change by 2, and it has from -1 to +1. Double checking 0 and 0, carbon, carbon, plus minus for 2 bonds to O, and minus plus for the bond to H. So plus, plus, 0, and minus, overall +1. Hopefully this seems okay. If this is getting oxidized, then something else has to be reduced. So if I'm doing this in OChem, I'm going to use CrO3 with HCl, pyridine, just like we did up here, works. If you're doing this in biochem, then whatever I use, so NAD plus, the one pouring H, it's going to pick up an H, that will work. The H it's going to pick up, I assume, is going to be this one. So that H right there will become that H right there. And this H right here will become the acidic proton that falls off. Okay. Hopefully this seems reasonable to you. Other reactions. Bio, the side chain of cysteine is a thiol. The 2 thiols can go in this direction, so you have to look at this and figure out what has happened. Have you gained or lost O's? Nope. Have you gained or lost H's? Yes. I lost H and H. Loss of H is oxidation. Here, I can do it by formula. It's gone from 6 H's to 4, 2 O's to 2 O's, so this one has loss of H as well. So loss of H means oxidation. So whether I do it by seeing the atoms disappear, seeing the formula, or actually seeing the bonds change, you need to recognize gain of H, reduction, loss of H, oxidation, gain of O, oxidation, loss of O, reduction. Okay, so those are some oxidation reactions. Let's see if we can recognize both. So in this case, 1 bond to O from a carbon to 2 bonds O. You increase your bonds to O, you've been oxidized. You've carbon, carbon, carbon chain. Here you have a carbon with 1, 2, 3 bonds to O. Now that same carbon only has 1 bond to O. From 3 bonds to O to 1 bond to O, you have lost bonds to O. Lose bonds to O, you have been reduced. From this compound, 1, 2, 3, 4 bonds to O to 1, 2 bonds to O. Going from 4 to 2, you've reduced the number of bonds to O. You've undergone reduction. Next one up, 2 bonds to O to 3 bonds to O. You've increased from 2 to 3. You've gained a bond to O. You have been oxidized. And if you're really good, you have been oxidized by 2, reduced by 4, oxidized by 2 at each carbon for overall 4. You have been oxidized, excuse me, on this one. Here you've been reduced by 2 at each, so reduced by 4. Here you've been 2 to 3, lost bond to H, so two electrons. It's almost always two electrons when we deal with alchem. Very, very few examples that are not. We've gone from 2 bonds O to 1, 2, 3, 4. So gain to O, that's been oxidation. Here we've gone from 1, 2 bonds O to 1. 2 to 1 means we reduced, so we lost bonds O. Reduction. This one's a little bit tricky. So this is why I have to just consider nitrogen a little bit, but 1 bond to a more electronegative atom and 2 to more electronegative atom. So you can think of it, an N and an O are both more electronegative. So what would happen here? From 1 bond O to 2 bond O, we already did that. We said it was oxidized. So it gains bonds to a more electronegative atom. So gain bonds to a more electronegative atom, which means it has been oxidized. And then finally, I go from 1, 2, 3 bonds to a more electronegative atom to 1, 2, 3. Broke even, 3 and 3. No change in the number of bonds to electronegative atom. This is just known as hydrolysis. It's not redox. So I should probably make note of that. This is hydrolysis. Water is not an oxidizing agent. So hydrolyzing something simply changes the bonds, but it does not oxidize or reduce it. Okay, to be more specific, I also should make note, you lost H. You had a bond from H here, it's gone. On this one, you had 3 bonds O, no bonds H. Now you have a bond O and 2 bonds H. So you also gained H. It's got reduced. This one, you had no H's here. Now I have an H here and an H here. So I take that. You had 1 here, but it gained H. This one, this H here is gone, so it lost H, oxidation. This one here, it gained a bond to H. This one here, this is a little tricky. No change in any of it. And I really should point out that this one up here, it didn't actually lose an H. It looks like we inserted an O, just like it looks like we inserted O here, so I've ignored them. But I did lose a bond to H. And this one I lost a bond to carbon. So that's a little different. This one lost a bond to H. So that also qualifies as oxidation. This one, no bonds to H or having gained or lost. So no reaction, redox reaction at least. Okay, some common organic reducing agents. You got to know these. Mentioned that list before, if it has rich in O, it's an oxidizing agent. Rich in H, it's a reducing agent. There are 2 we typically use, and these 2 we vary to such an extent that we turn them into about 1 million different compounds, but they're all rooted in the same basic notion. H on a metal, H is a more electronegative, so we call these hydrides because they are negative H's. Very rare. This is called lithium aluminum hydride, and this is called sodium borohydride. Lithium because that's kind of balances it out. Sodium because that's the one we typically use. So NaBH4 and LiAlH4. Depending on who your teacher was, they may simply just call this LaH, lithium aluminum hydride, and NaBH4 or NaDH. That's not as common, but LaH, you may just hear that. Okay, so this H minus hydride is a great nucleophile. Keep in mind, minus finds plus. So if I have a minus on that H, if I have delta minus on that, then I have a delta plus here. Minus is going to find H. That's a 5th bond, so that pi bond has to break. So let me get rid of that and show how this works. So I'm going to use sodium borohydride in this case. This negative H is going to come in and attack. When it does, it's going to kick those electrons up, as mentioned. You're going to end up with this H now bonded there and a BH3, which is reasonably stable. This O can't really come in and kick out any of these leaving groups, so we end up just protonating it. So it has to react in some sort of protic environment to pick up an H to become neutral. So when it does, you're going to end up with that species. Trick is, if it's a little too protic, we have an issue, but it has to be just protic enough. So can't have it be an acidic compound, that'll ruin the species. But if you have it just protic enough, so methanol, for instance, might be a good solvent for this one. And you end up getting methoxy side chain. Okay, so far so good. Not sure why I put this in here other than to keep track of all the molecules that are coming in. The O eventually is going to find that pH 3, so I could have drawn it there just as easily. So this pH 3 is the same as this one. It wasn't newly formed. O comes on, you start getting a borate. Now this compound still has H's to deliver. They won't be as good. The first one is going to be the best one delivered. This one's going to be a little less reactive. So depending on your carbonyl, if it's not very reactive, you want to put a high amount of BH4 in there. If it's a little more reactive, then I can get away with using maybe a 2-to-1 or 3-to-1 or 4-to-1 ratio and take advantage of all those H's. So we will get into that more and more as we get deeper into this. I'm going to just go with BH4 and ALH4 as my typical ones. And when I mentioned the millions, and I exaggerated, but there are hundreds of variations on this where they put some of these groups on here already to control its reactivity. So to make it so it reacts with one carbonyl and not another. So if you have a compound that has like 9 carbonyls on it, if you want it to react with the least reactive one, then you put an already spent boron on there. So there's so many different versions that we're going to discuss as we go deeper into this. But for now, 4H's and 4H's, that's what we're going to learn for this podcast. And if you will, this semester or quarter if you're in the class. Okay, esters. Sodium borohydride, because aluminum is less electronegative, it gives up H more easily, so it's more reactive. Boron, because more electronegative, kind of holds onto the H a little more tightly. Esters, because of resonance, are more stable and less reactive. So esters will not react with this. So this compound, the sodium borohydride, can only react with ketones and aldehydes. And that's an embarrassing drawing, those ketones. I don't know if that's any better, but ketones and aldehydes, lithium hydride can react with ketones and aldehydes, but also carboxylic acids, esters, lactones. It can react with a far greater number of compounds. But the same thing's going to happen. It's going to come in. But now the difference is this can kick in and kick out that leaving group. So when it does, it turns this aldehyde. But like I just mentioned, this can also react with aldehydes. So it is possible that it can react again and reduce it all the way down to a primary alcohol, which will pick up this H. So if you have 3 bonds to O, you can reduce it all the way down to 1 bond to O. So it's going to get doubly reduced. Okay, fairly important. This is a key thing to note when it comes to reactivity, where if you want to poison it along the way, that's when we start using specialty versions. ALH4, aluminum hydride, will go all the way to the alcohol. But if you start putting less, like 3 R groups on here or OR groups or something that will reduce the reactivity of aluminum, then you might be able to limit it to stop at this. So we make molecules that are a little less reactive, so it targets and doesn't go beyond that. Okay. Which is the strongest reducing agent? So we should know reducing agents get oxidized. Reducing agents are rich in H. So by virtue of being rich in H, that one should be gone. And you should know that H on a electronegative atom will be H plus. That's not going to work. But the two I've memorized, lithium hydride in an ether, sodium borohydride, in this case, an ether. Could be an ether, could be methanol, different solvents it can work in. But pour an H, so that one won't work. And ammonia, again, H on a high electronegative atom is going to be, it's going to act like I mean, more acidic, even though this is a weak base. It's just not going to do much of anything. So again, this is that random fun fact just mentioned. I want to reiterate. As you go down, things get less electronegative. Less electronegative means it won't hold on to electrons as tightly. So aluminum, being less electronegative, gives up H minus more easily. So NaBH4 only reacts with aldehydes and ketones. Lithium hydride reacts with everything. So this is more reactive. This boron is less reactive. So this is a mild reducing agent. This is a strong reducing agent. Knowing the nuances matters. Okay, so lots and lots of information thrown at you. This is one of those, hopefully you took good notes. Got to do questions. As soon as you do questions, the better. And some of the questions hopefully will focus on deciding which reagent you need, whether it's an aldehyde or ketone. Don't overdo it. Use the weakest one that'll get it done. So I'm going to mention something, and I'm going to repeat this a lot, and that is, chemists, we're not the, I don't know, we're not the go-getters. We're the ones who just sort of cruise. Like, why do the high road when the low road gets you where you need to go? So aim low, barely get it done. If you use something too reactive, it reacts too much. Find the one that barely gets it done. So if you have an aldehyde or ketone, absolutely no need to use anything strong like lithium hydride. Just get by with sodium borohydride. But if you need a stronger reagent, use a stronger reagent, but use one barely strong enough so you minimize your side products. Aim low, be lazy. Okay, that covers it. So thank you for once again sitting through. So I will see you at the next podcast. Bye.